Recall electron withdrawing substituents have a great effect on acidity. The stronger and or closer they are to the acidic proton, the stronger the acid. So we can see as we add more functional groups on here, the stronger the acid. Electron withdrawing substituents affect benzoic acid as well. So here are some electron withdrawing substituents. You can see how the effect on the pKa is affected by them. So have a review. So if you want to review some of the previous methods for preparing carboxylic acids, please refer to sections 9.9 or 12.1. And there are also some preparation on 17.6. So two more reactions that produce a carboxylic acid. So we have the hydrolysis of nitriles. This allows a two-step synthesis of a carboxylic acid from an alkyl halide. And we also have the carboxylation of a Grignard reagent. This gives us a second method to convert an alkyl halide into a carboxylic acid in a two-step synthesis. So we can see this two-step synthesis right here, step 1 and then step 2. Carboxylic acids can be reduced to a primary alcohol with lithium aluminum hydride. Just imagine that this hydride is going to come in right here. Okay, so in this case, it's going to deprotonate the base first. Put the electrons on the hydrogen. Let's see what's going on. And so the carboxyl is reduced to an aldehyde first. So I had that wrong. So it's going to deprotonate that proton first. Another hydrogen is going to come in here. It's going to form the aldehyde, and the aldehyde is then reduced to the primary alcohol. So once again, we can see that we see the deprotonation. H2 will form a gas, so it'll readily be expelled. Then we have the reduction of the carboxylate to an aldehyde. Now that proton's going to come in here, and it's going to simultaneously grab that aluminum dihydride. We have our aldehyde, and the aldehyde is reduced to the primary alcohol. So BH3 can be used instead of lithium aluminum hydride and is chemoselective for the carboxylic acid. Chemoselectivity of BH3 allows for the reduction of a carboxylic acid in the presence of an ester. It's not touching this group over here. This group stays. This group is being reduced. It says, note the reduction of a carboxylic acid involves a change in the oxidation state. There are also many reactions which carboxylic acids don't change the oxidation state if Z is the hetero atom. So in the bottom case, we're not changing the oxidation state, are we? Most common carboxylic acid derivatives are shown here. Any compound where carbon has 3 bonds to the electronegative atom is a carboxylic acid derivative. So here we see a nitrile. So acid halides and anhydrides are relatively unstable and are not common in naturally occurring compounds. Ester and amides are abundant in nature. So they're showing you some esters and amides are esters that are abundant in nature. Proteins are comprised of repeating amide linkages. To name an acid halide, replace IC acid with YL halide. So acetic acid becomes acetyl bromide, and benzoic acid becomes benzyl chloride. If an acid halide group is connected to a ring, the suffix carboxylic acid can be replaced with a carbonyl halide. Let's see. Acid anhydrides are named by replacing acid with anhydrides. So you can see this acetic anhydride, and we can see succinate anhydride on the bottom. And these are symmetrical anhydrides. You can see they're symmetrical, and there's also asymmetrical anhydrides. And here's one which is called acetic benzoic anhydride. Esters are named by naming the alkyl group attached to the oxygen, followed by the carboxylic acid's name with the suffix -ate. So acetic anhydride, or no, acetic acid becomes ethyl acetate. Melanic acid becomes diethyl melanate. Esters are named by naming the alkyl group attached to the oxygen, followed by the carboxylic acid's name with the suffix -ate, so ATE. we see we have cyclohexane carboxylic acid. And here we see we have methyl cyclohexane carboxylate. Amides are named by replacing suffix IC or OIC acid with amide, so acetic acid becomes acetamide, benzoic acid benzamide. Amides are named by replacing the suffix. So we have cyclohexane carboxamide. So if the nitrogen atom of the amide group bears alkyl substituents, their names are placed at the beginning of the name with N as their locant. So here we have N-methyl acetamide, and here we have NN dimethyl acetamide. Nitriles are named by replacing the suffix IC acid or OIC acid with O-nitrile. So aceto-O-nitrile, and then we have benzo-nitrile. So carboxylic acid derivatives are electrophilic at the carbonyl carbon. The reactivity is determined by induction, resonance, sterics, and the quality of the leaving group. So we have the most reactive leaving group, which is chlorine. The least reactive would be the NH2 group. Acyl chlorides are the most reactive derivatives. So we have induction. The electronegative chlorine enhances the electrophilic character of the carbonyl. And we have resonance too, where the chlorine atom does not donate much electron density to the carbonyl carbon. The chlorine does not significantly donate electron density to the carbonyl. So this is not a significant contributor right here. It says amides are the least reactive acid derivative. Examine the okay, we have induction. The nitrogen atom is less electronegative than chlorine, and the nitrogen atom contributes significant electron density to the carbonyl carbon. Aldehydes and ketones are also electrophilic, but they do not undergo substitution. And carboxylic acid derivatives undergo nucleophilic acyl substitution. Nucleophilic acyl substitution, the general mechanism, so we have a nucleophilic attack followed by the loss of a leaving group. So we have a really good leaving group right here with the chlorine. We have a nucleophilic attack, and we have the loss of the leaving group. So understand the nucleophilic acyl substitution is not an SN2 mechanism. And sometimes a proton transfer will be necessary in the mechanism. So all the participants, a reaction mechanism, so should be consistent with the conditions employed. So they give us a specific example where acidic conditions are used. So the first step will not be a nucleophilic attack because a negatively charged oxygen will not be produced under acidic conditions. So the first thing is there's going to be a proton transfer with the ketyl group right here. There'll be a proton transfer. And I show that on the next slide right here. Pronation is generally always the first step in an acyl substitution mechanism under acidic conditions. So once we have that pronated, we can have a nucleophilic attack on the pronated carbonyl. So under basic conditions, the carbonyl is not protonated first. The strong nucleophile would attack first. So that's the difference between the basic and the acidic conditions. So when an amine is a nucleophile, it will attack the carbonyl first without the carbonyl being protonated first. A tetrahedral intermediate with both positive and negative charge forms. And we can see that here. Just to be sure to avoid drawing intermediate with two charges of the same type when drawing. So just try to avoid the intermediate with two different charges. Since proton transfers are utilized in the mechanism to remain consistent with the conditions employed, under acidic conditions, up to 3 proton transfers are necessary in the mechanism. So you get to be a decision maker. It says consider the mechanism for the following reaction. The conditions are not acidic. The carbonyl is not protonated first. So we have a nucleophilic attack followed by a loss of a leaving group and then followed by a proton transfer. All right, so we have to consider the leaving group. So consider the mechanism following the following reaction. The leaving group does not require protonation in order to leave, but there is a proton transfer at the end. So we have a nucleophilic attack followed by the loss of the leaving group, and we have a proton transfer at the very end. It says consider this mechanism for the following reaction. This pattern is typical for reaction of acid halides. So an acid chloride is synthesized from a carboxylic acid using SOCl2. The mechanism is split into 2 parts. We have a nucleophilic attack, followed by the loss of a leaving group, and then we have a proton transfer. If you want to see this mechanism, we can see it here. It also a good resource would be page 918. So this is part one. Now we've established an excellent leaving group right here. Part two. So the second part is a typical nucleophilic acyl substitution. So the first part of the mechanism converts the OH group into a better leaving group, which is accomplished in 3 steps. So part two of the mechanism is a typical nucleophilic acyl substitution, which is accomplished in 2 steps. First, we have a nucleophilic attack, followed by a loss of a leaving group. In this case, the leaving group further degrades to form gaseous SO2. So this is gaseous SO2 right here. Oh. Which leaves the reaction mixture which forces the reaction to completion. So when reacted with water, an acid chloride is converted to a carboxylic acid. So a nucleophilic attack, so water, functions as a nucleophile. We have a loss of a leaving group. The carbonyl group is reformed, and a proton is removed to generate the carboxylic acid. So these are the same 3 steps that was just used in the prior mechanism, right? This reaction produces HCl as a byproduct, and the HCl can often produce undesired reaction with other functional groups that might be present in the compound. So pyridine is used to remove the HCl as it is produced. So we see right here that pyridine is usually used to neutralize it. So when treated with an alcohol, let me see. So acid chlorides are reacted with an alcohol to make an ester. So when treated with an alcohol, acid chlorides are converted into esters. The accepted mechanism for this transformation is directly analogous to the mechanism that we presented for hydrolysis of an acid chloride, which was through a 3-step mechanism. And pyridine is used as a base to neutralize the HCl as it is produced. So when we show the reaction like this, the OH group is said to undergo acylation because an acyl group has been transferred to the OH group to produce an ester. This process is sensitive to steric effects, which can be exploited to selectively acylate a primary alcohol in the presence of a secondary, more hindered alcohol. So acid chlorides are used to synthesize amides, and pyridine is not used to mop up the HCl byproduct here. Instead, 2 equivalents of the mean are used. So each one of these mechanisms, there are generally 3 steps. You have a nucleophilic attack, followed by the loss of a leaving group to reform the carbonyl. And the 3rd step is usually a proton transfer to remove the positive charge. So now let's look at the study of the reduction of acid chlorides. So acid chlorides can be reduced using lithium aluminum hydride to form a primary alcohol. So the lithium aluminum hydride, it delivers a hydride ion which attacks the carbonyl group, and we can see that right here. The carbonyl group is reformed. So we have a loss of a leaving group, followed by a nucleophilic attack, and then a proton transfer. So the first two steps of this mechanism are probably exactly what you might have expected. The nucleophilic attack followed by the loss of a leaving group to reform the carbonyl. These two steps produce an aldehyde, which can be attacked again to give an alkoxide ion. The alkoxide ion produced after the second attack does not have any groups that can leave, and therefore nothing else can occur until a proton source is provided to protonate the alkoxide ion. You can see that proton source right here. This reaction has little practical value because acid chlorides are generally prepared from carboxylic acids, which can be simply be treated directly with lithium aluminum hydride to produce the alcohol. So by using lithium tri-T-butoxy aluminum hydride instead of lithium aluminum hydride, the reduction can be stopped at the aldehyde. So if you want to stop it at the aldehyde, please use this reagent. So an acid chloride can be reacted with a Grignard reagent to form a tertiary alcohol. So just as with the lithium aluminum hydride, two separate steps are required. First, the acid chloride is treated with the Grignard reagent, and then the proton source is added to the reaction flask. Water can serve as a proton source, although the H3O+ can also be used in the mechanism. So we see we have a nucleophilic attack, followed by the loss of a leaving group. We have a second nucleophilic attack, followed by the proton transfer. But the reaction between an acid chloride and a Grignard reagent cannot be used to produce a ketone. Using one equivalent of the Grignard reagent simply leads to a mess of products. Producing the ketone requires the use of a more selective carbon nucleophile that will react with acid chlorides, but not with ketones. And there are many such reagents. The most commonly used reagent for this purpose is lithium dialkyl cuprate, also called a Gilman reagent. And we see a Gilman reagent right here. So then you can have some reaction of acid chloride to a summary, and this summary is provided on page 922. So anhydrides can be synthesized by excessive heating of a carboxylic acid. This method is only practical for acetic acid you see right here, as most other acids cannot survive the excessive heat. As we might expect, this process occurs via a mechanism with two steps. We have a nucleophilic attack, followed by the loss of a leaving group. And this method can be used to prepare symmetrical or unsymmetrical anhydrides. So welcome to the study of the reaction of acid anhydrides. So given that they both contain good leaving groups, the reactivity of anhydrides is analogous to acid chlorides. So when acid chloride, the leaving group is a chloride ion, right? And the byproduct of the reaction is therefore HCl. With an acid anhydride, the leaving group is a carboxylate ion, and the byproduct is therefore a carboxylic acid. So as a result, it is not necessary to use pyridine in the reaction with acid anhydrides because HCl is not produced. So we're not producing HCl with this. And here, this figure can be found on page 923. So note that each of these reactions produces acetic acid as a byproduct. So for this reason, acid chlorides are more efficient as starting materials than acid anhydrides. So acetic anhydride is often used to acetylate an amine or an alcohol to make an ester or amide. Acetic anhydride is commercially used to synthesize aspirin and Tylenol. And aspirin is prepared from salicylic acid, a compound found in the bark of the willow tree that has been used for its medicinal purposes for thousands of years. Esters can be prepared by SN2, so an SN2 reaction is concerted. So Fischer esterification combines a carboxylic acid and an alcohol using an acid catalyst. The mechanism is consistent with the one that occurs under acidic conditions. So we're going to look at the mechanism here. So we have a proton transfer, followed by a nucleophilic attack, followed by another proton transfer, a third proton transfer, a loss of a leaving group, and a fourth proton transfer. So I'll leave this up for a minute. So I think this is a good time to take a break. So let's go ahead and take a 10 to 15 minute break. I'm going to leave this up here, and I'll see you in about 10 to 15 minutes. All right, everyone, welcome back. Hopefully everyone enjoyed their break. We left off on mechanism 2010. So hopefully you had enough time to soak that in. So we will go to the next slide then. So now we go to isotopic labeling. The mechanism for the Fischer esterification reaction is supported by an isotope labeling experiment. So basically they're labeling that oxygen to see where that oxygen is moving. Esters can also be prepared by treating acid chloride with an alcohol. We can see this right here. Esters can undergo hydrolysis under basic conditions. This is called saponification. This is how you can make soaps. And let me see what page they put that on. So this is on page 927. So saponification, you have this ester group, and we're gonna make this carboxylic anion or ion. And these are used in soap. So we have a nucleophilic attack, followed by loss of a leaving group, and then a proton transfer. Esters can be hydrolyzed under acidic conditions. We can see the hydrolyzation of this. Here's a mechanism for ester hydrolysis mechanism. We have a proton transfer. Create a positive charge here. Someone may ask, well, why? It's 6 minus 5, that's +1. Followed by a nucleophilic attack. Then we have another proton transfer. And we have another proton transfer. So here's our third one, followed by the loss of leaving group. And then we form our carboxylic acid group right there. Immunolysis, esters can also undergo immunolysis to form amides. This is in section 2011. Esters can be reduced using reagents such as lithium aluminum hydride. ester reduction mechanism. This is a nucleophilic attack followed by loss of a leaving group, a second nucleophilic attack followed by a proton transfer. So reduction of an ester can be stopped at an aldehyde by using DIBAH. That's your diisobutyl aluminum hydride. So you have two butyl groups here. You count, there's 4. So that's your diisobutyl aluminum hydride. So esters can also react with Grignard reagents to form a tertiary alcohol. And we can see that right here. And they show that in mechanism 210, which is on page 931. So this reaction is analogous to the reaction of an acid halide with Grignard reagents. We have a nucleophilic attack followed by the loss of a leaving group, a second nucleophilic attack followed by a proton transfer. Amides can be made from any of the carboxylic acid derivatives already discussed. Here's your least reactive, here's your most reactive, really good leaving group. The most popular way to make an amide is from an acid chloride and the corresponding amine. Remember, 2 equivalents of the amine are necessary. 1 full equivalent is neutralized by the HCl byproduct from the reaction. Amides can be hydrolyzed with an acid. The reaction is slow and requires high temperatures though. And they're going to they show the reaction right here where we have a proton transfer. We'll go back to this slide. The products are favored at equilibrium because the NH3 group is protonated and is not capable of acting like a nucleophile in the reverse direction. And they show the mechanism here. This mechanism can be found on page 933. Over proton transferred, followed by nucleophilic attack, followed by a second proton transfer. Then this NH3 group is going to have a proton transfer. We have a loss of a leaving group, the amino group, and then we form our carboxylic acid group. So under basic conditions, amides can also be hydrolyzed. The base catalyzed hydrolysis is even slower than when acidic conditions are used. The mechanism is analogous to the base catalyzed hydrolysis of an ester, which we've looked at. So you're going to have a nucleophilic attack followed by the loss of a leaving group, a proton transfer, and that will be it. And I show that on this slide right here. So amides are reduced to the corresponding amine with lithium aluminum hydride. So the carbonyl group is completely removed while the nitrogen remains bound to the molecule. Recall when a primary or secondary alkyl halide is treated with a cyanide ion, the cyanide acts as a nucleophile in an SN2 reaction. And nitriles can also be made by dehydration of a primary amide using a variety of reagents, including SOCl2. Which is thionyl chloride. SOCl2 is thionyl chloride. So we have the amide function of the nucleophile and attacks the thionyl chloride. We have a loss of a leaving group, proton transfer, followed by another proton transfer. So I'm going to leave that mechanism up so you can see it. So nitriles can also be hydrolyzed under basic conditions. And the next steps are going to show you under the basic conditions then, right here. Nitriles are hydrolyzed to carboxylic acids under acidic conditions. Again, acidic workup is necessary to obtain a carboxylic acid because basic conditions otherwise yield a carboxylate ion. And that mechanism is shown here. And if you further information about this mechanism can be found on page 936. I mean, it's the same thing. You have a protonation. A lot of these follow the same type of concepts, followed by nucleophilic attack, a proton transfer, another proton transfer. So you have 4 proton transfers. Nitriles can also react with Grignards to form a ketone. So after the nitrile reacts with the Grignard, an acid is added to form an amine, which is then hydrolyzed with excess H3O plus to form the ketone. So this is similar to how carboxylic acids can be converted to alcohols using lithium aluminum hydride. Nitriles can be converted to primary amines. So then they give you some steps or some helpful strategies. When designing a synthesis, stick with the same strategies with any synthesis discussed earlier. Is there a change in the carbon skeleton? Is there a change in functional groups? And there are many new functional group transformations in this chapter that we've talked about. We've talked about all of these. Let me see. So the figure is organized according to oxidation state. Further reading about this can be found on page 938. So carboxylic acids and the derivatives all have the same oxidation state and are shown at the top of the figure. Aldehydes exhibit a lower oxidation state and are therefore shown below the carboxylic acid derivatives. So 2 kinds of carbon-carbon bond forming reactions covered in this chapter. We've covered these. But it's useful to recall a carbon-carbon bond forming reaction from section 1312, which moves the functional group by 2 atoms. You want to put the so when forming new carbon-carbon bonds, it is critical to install functional groups in the proper location. Then they're going to go over some IR spectroscopy of where you might find these on an IR spectrum. So recall that conjugated carbonyl signals appear at a lower wave numbers than the saturated. So the OH stretch of an acid gives a very broad peak. The carbon a triple bond to the nitrogen appears around 2200. The carbon-13 peaks appear around 160, 185 on a carbon-13 NMR. Nitrile carbon-13 peaks appear around 115 to 130. And when looking at proton NMR, the peak for a carboxylic acid proton appears around 12 ppm. So that's really downfield. That's it really for the study of carboxylic acids. I think we've learned a lot today, so we're going to end it here today. We'll continue on tomorrow with the chapter 20 homework. Have a great day, and I'll see you tomorrow.